In our previous video, we built the idea of velocity, constant velocity in particular. But velocity doesn't need to be the same all the time. Velocity can change over time, just like position can change over time. And usually this is really the default behavior. Things don't always go the same speed. They change all of the time. Okay? So what we're going to look at here is we're going to build up the idea of changing velocity. What happens when velocity changes? We have our definitions already. So similar to how we built the idea of velocity out of changing position, we're going to build our next concept out of the idea of changing velocity. So I'm going to start out with a graph. All of these definitions come from graphs. So we're going to start out with a very simple graph, but this time we're going to plot our velocity. How fast and in which direction is the object moving? We're going to use our units, meters per second. We're going to plot that against time in seconds. This is a velocity time graph. Velocity versus time. How does the velocity vary in time? I'm again going to take a very simple example, the simplest possible example. If I can make my ruler cooperate. Having trouble. I'm going to put my points in so I can see them better. I'm cheating, putting my points in first and then drawing the line. There we go. So we're going to take a very simple example. The object begins stationary and it speeds up in a uniform way so that it looks like this. So we know that at 1 second it's moving at 1 meter per second. At 2 seconds it's going 2 meters per second. At 3 seconds it's going 3 meters per second. This is not constant velocity. It's changing. However, it's linear. So just like in the previous case when we had a position versus time, we're going to look at changes. How does velocity change? What is the change in velocity between 2 points? Let's again go from 1 second to 2 seconds. All changes are subtraction problems. So we take the second velocity, subtract the first velocity. Looking back at my graph, I can see, okay, at 2 seconds the object was going 2 meters per second. At 1 second it was going 1 meter per second. That is a change of 1 meter per second. The object is going 1 meter per second faster than it was previously. So we now have the idea of changing velocity. There's no special word for this. To review, a change in position is called displacement. We could make up a word to represent change in velocity. We don't. We just call it change in velocity. How do you calculate it? Take the velocity later, subtract it from the velocity earlier, and that tells you your change. Let's look at the slope. In physics, slopes generally have meaning. So let's look at the slope of this one and see what it can tell us. We're familiar with the slope equation, y2 minus y1. But in this case, the y values are velocities. So we're going to take our second velocity, subtract our first velocity, over, so delta y over delta x. But x, those are times. So we're going to take our second time, subtract our first time. We have data points for this. Looking back, our second one first, we have time of 2 seconds, a velocity of 2 meters per second, minus at 1 second, the object was going at a rate of 1 meter per second. Simplifying this down, 2 meters per second minus 1 meters per second is 1 meter per second. 2 seconds minus 1 second is 1 second. Simplifying that a little farther, we find that the slope of our line is 1 meter per second per second. That's a little weird. meter per second per second. It sounds like you got an echo or a stutter or something going on there. But this is actually very meaningful. As time progresses, for every 1 second that passes, we gain 1 meter per second. Let's go back and look at the graph. This is a slope. If we go over 1 second, we gain 1 meter per second. Over 1 second, gain 1 meter per second. Over 1 second, gain 1 meter per second. This is a case where our velocity is changing at a constant rate. Our velocity is changing at a constant rate. Well, we did a trick last time. Last time we took the slope of our position versus time graph, we found that it told us something useful, we gave it a name, we called it velocity. This time we took the slope of our velocity time graph and it tells us something useful. It tells us the rate at which our velocity changes. So let's write that down. The slope tells us the rate at which velocity changes. That's useful if I know how fast it's going now, and I know how fast it's going to be going, or I'll be able to predict how fast it's going later. Okay? This has a name. We call this acceleration. We call it acceleration. It has direction. The slope of this line is positive. It could have just as easily been negative. If the slope were negative, the acceleration would be negative. This is a directional concept. It's a vector. It has a symbol. There's the symbol. It has a definition. This is the slope of the velocity time graph. That gives us the equation. We know the slope formula. Acceleration is the slope. Change in y on a velocity time graph, our y values are velocities. Change in y over change in x, which on our graph is time. Our y values are velocities, our x values are times. So our equation for acceleration is this. This is the definition. In this case, when our velocity time graph is linear, when that's the case, we call this constant acceleration. That is the full scope of this course. We could go ahead and repeat this exact same thing. Do it again. Make an acceleration time graph that is linear. That means the acceleration is changing at a constant rate. That also has a name, and if you care to know, that name is jerk. It's called jerk. Didn't make it up, just conveying the information. However, that is beyond the scope of this course. The farthest we need to go is to this idea of constant acceleration. What does that mean? It means this. It means the velocity changes in a uniform way. The velocity versus time graph forms a straight line.